of you uh, and for joining us here. And what we're going to do tonight is we have a wonderful speaker. We have Professor Brodney Fitzgerald from Grossmont College with us this evening. So very excited to have him here. And then we're going to start off with some astronomy news updates. If you have any questions for us whatsoever, please put them in the Facebook chat and I will answer them for you or I will answer them for you or Professor Fitzgerald will answer them for you. So let's go ahead and get started with some news. The first bit of news I want to mention is that Astronomy on Tap will be back in October. On October 4th at 7:30 p.m., Professor Scott Cardell from Palomar College will be joining us to talk about observing with smart telescopes. And if we're lucky and the weather cooperates, we'll even do some observing during the event. And so that's our goal for our October version of Astronomy on Tap San Diego. Still going to be virtual, still going to be live here on Facebook. Now let's talk about some current astronomy news before we get into tonight's topic about the JWST telescope. First of all, it's September, which means we're heading from summer into fall. And I just want to remind you that fall happens in around, the fall equinox happens around September 21st every year. I just want to remind you, though, that distance is not the reason for the seasons. This is an image of the sun taken with the same telescope with the same camera. And you'll notice that the sun looks larger in January and smaller in July. And that's because we're actually closest to the sun in January and farthest from it in July. And so that might surprise some of you. But this, I think, helps a lot. These are images of the Earth from space on the solstices and the equinoxes. And equinox means equal night. So the idea there is that we get equal hours of daylight and darkness on the equinoxes. Because the Earth's tilt isn't pointed towards the sun on those days or away from the sun on those days, it's actually parallel to the sun. And so we get parallel lines of sunlight coming in. So just a reminder, it's the tilt of the Earth, not the distance from the sun. That is the reason for the seasons. And another thing that's been in the news is the Artemis spacecraft. Artemis is NASA's next attempt to go to the moon. And so we don't have any Saturn V rockets left anymore. And so this is a new launch vehicle for moonshot attempts. And you may have heard there's been a couple of scrubbed launches. The first time was because one of the engines was not getting up to the right temperature. And the second time, it appears that there was a fuel leak. We actually could not get the spacecraft off the ground on either of the launch dates. And I know that often sounds like a failure, but I think what we have here is an example of how the procedures worked. These are really big rockets, and we don't want them to get off we want them to launch safely. And so the procedures, they caught the problems before the launch happened and something bad happened. So as much as we want to see these spacecraft get off the ground and we'd like to think everything works smoothly, things tend not to work smoothly the first time. And so we're going to consider these successes from the point of view of making sure it gets the job done. And then one spacecraft mission that you might not have heard about, but that I'm actually kind of excited about because I like cosmic collisions. NASA's DART spacecraft is approaching an asteroid. It's actually approaching the asteroid Didymos, and it has a little moonlet that orbits it called Dimorphos. And this spacecraft is going to actually run into the small moonlet. And the reason for that is that this asteroid presents no threat to the Earth whatsoever. However, what they're doing is testing what we could possibly do to see if we could deflect an asteroid if it was approaching the Earth. So, because lots of times, when we take a look at these movies where we talk about, okay, like, well, what could we do if an asteroid was coming in? Maybe we could just blow it up. Then we just get hit by lots of bits of asteroid instead of one big asteroid. What we have going on here is a test of what is a more feasible way to divert an asteroid coming in, which is gently nudging it out of the way when it's far enough away that a small deflection to its orbit would mean it would miss the Earth. So this is supposed to happen later this month. And if it does, we'll tell you all about it at the Astronomy on Tap in October. And so those are just some things going on in astronomy news right now. Now it is my privilege to introduce Professor Brodney Fitzgerald of Grossmont College and a longtime City College colleague as well. And I'm so glad he has decided to join us tonight. So I'm going to stop sharing so that he can share his screen and he can go ahead and get started.
All right, thank you so much, Lisa. Alrighty, so we'll share. Alrighty, so I'll go and get started. So my talk is going to be on the James Webb Space Telescope. And so it's going to be the past, the present, and the future. So it represents the new eye of the cosmos. And so this particular picture you're seeing here is a combination of a Hubble image and a JWST or James Webb Space Telescope image of the same part of space called the Carina Nebula. So it's about 7,500 light years away from the Earth. And one of the things I'll talk about is notice the contrast between the Hubble image on the left and the much more detailed image on the right-hand side. And I'll talk about how that has something to do with the type of light that the James Webb looks through. Alrighty, so the agenda for tonight, so I'll do a little bit of background information on telescopes in general, as well as the nature of light. Then I'll go into talking about a little bit about the Hubble Space Telescope, as well as some images from the Hubble Space Telescope, so representing the past. And then I want to end by talking about the JWST, the present and the future information and images. So as far as telescopes are concerned, in astronomy, we have two major types of telescopes. We have the refractor telescope, which just means the light bends as it focuses in using two lenses. So you have the bigger lens where the light comes through. Then you have your smaller eyepiece lens at the end for the refracting telescope. Now, most of the time actually all the time for the space-based telescopes, all of them are of the reflector telescope type. That is, they use mirrors to actually focus the light from their source, whether it's a star or a galaxy or even a planet's atmosphere. We use reflectors for our space-based telescopes. So the little bit about the nature of light. So telescope is a very important instrument in astronomy, one of the most important instruments that we have. Another instrument that we have is, well, how do we figure out, say, the energy of a star or how massive a galaxy is? Well, we have to somehow study the light that they emit. So Sir Isaac Newton, way back when, before he invented the Fig Newton, just kidding, he didn't do that. In any case, the white light, so sunlight actually goes through this multi-sided piece of glass, which is called a prism. And out the other side, what he expected to get was essentially just the light bending or refracting, and you get white light out the other side. What he was able to prove, everyone, is that white light is actually a combination of all the colors, or Roy G. Biv, the colors of the rainbow. And you can actually study these individual colors, as you see here on the right, and they represent different wavelengths of light. Now, of course, some of you may recognize this picture from a particular album cover or a particular band. Feel free to put in the chat if you know which band I'm talking about for this particular picture. But that is the nature of light. So from the nature of light and by studying spectra, number one thing we can get is what the object is made up of, whether it's made up of hydrogen, helium, or some other elements. We can also figure out what the temperature of that object is. And thirdly, we can actually figure out the velocity of that object in relation to us. And so it turns out, everybody, that visible light is just a small part of the what's called the electromagnetic spectrum. So some of these forms of light you may be familiar with, for instance, X-rays at the dentist or at the airport. We're familiar with X-rays. For those of you who are She-Hulk fans out there or Hulk fans, you're familiar with gamma rays or other superheroes like the Fantastic Four. Gamma rays, they represent the highest form of radiation that we have, the highest energy form of radiation. Then you have microwaves, radio waves, infrared, as well as ultraviolet light. So the part that we can see with our eyes just represents that little small portion of the electromagnetic spectrum. And so what we want to do as astronomers is not just look at the visible light to figure out our information. We want to look at all the wavelengths, or as many wavelengths as possible, to actually study these particular objects, whether it's a star or a galaxy or a planet. So this will transition into talking about first the Hubble Space Telescope. So just a couple of facts about it. So it's launched and been out in space since, 1990, maybe older than some of the people out in the Facebook out there, 1990. And it's about the size of a yellow school bus, so pretty huge telescope. And as far as how long it takes for it to orbit around the Earth, it takes about 95 minutes to actually orbit the Earth. So to compare that to the International Space Station takes about 90 minutes to orbit the Earth. They both move around pretty fast around the Earth. And so I thought, as a little fun poll question, so on the next slide, I'll pose the question about, well, what is the speed of this Hubble Space Telescope? So here we go. So which value do you think is the closest to the actual average orbital speed of the Hubble Space Telescope as it goes around the Earth? What do we think?
And feel free to put your answer in the chat too.
Yeah, definitely.
All right, so I see votes coming in for 20,000 miles per hour.
20,000 miles per hour. Nice job out there. So it is 20,000 miles per hour, or as I like to call it, the same speed somebody goes on the freeway heading to LA in the I-5. Same speed. In any case, yeah, so pretty fast going around for the Hubble Space Telescope. So as far as some more information about the Hubble Space Telescope, as well as images, one of the most famous images taken by the Hubble Space Telescope is what is called the Hubble Extreme Deep Field. And so to kind of put things in perspective, here you're looking at pretty much all the points of light except for the ones that have the X's. Those are stars, but everything else represents a galaxy. So you have over 3,000 galaxies in this picture that you're looking at on this slide. And how much of the night sky does this actually take up? Well, what's amazing is that little area right here on this slide takes up about this much. So if you see this little gray square in the center that's labeled XDF for the extreme deep field, it takes up that amount of the night sky, everybody, as compared to the moon here. So 3,000 galaxies in that little square. Just imagine how many galaxies you have in the entire night sky. So something interesting to think about. It's one of those pictures that I say kind of put things in perspective for me. Okay, now we get to compare to the past to the present. So this image shows the mirror, the main mirror, the primary mirror of the Hubble, which is just under 8 feet in diameter, versus all the multiple mirrors, 18 to be exact, that make up the James Webb Telescope. And so in astronomy for telescopes, the main thing that we concentrate on, and when we think about telescopes, is light collecting area. The more light you can collect, the brighter the image, the more detailed the image, the more information you can figure out. While the Hubble at the time, first space-based telescope, had a pretty big collecting area of about 50 square feet, just under 50 square feet. This James Webb Space Telescope has a collecting area of over 270 square feet. I mean, a very huge telescope that we're dealing with the James Webb Telescope. And I talked about earlier with wavelengths in the electromagnetic spectrum. Well, it turns out for the Hubble, it took images in the ultraviolet as well as the visible and a little bit in the infrared. So and that's what's best about these space-based telescopes. You don't have to worry about our atmosphere at all. You just have to have it out in space, and it can take images in multiple wavelengths. But the James Webb, everybody, is going to look in visible light, and it's going to look in most of the infrared. And what's important about infrared? Well, it turns out that's how you can find, for instance, your younger stars, younger than what the sun happens to be. You can also find planets that are outside of our solar system, and things that are a lot cooler than your normal stars, like the sun. So now some JWST info. So this image shows the James Webb orbit. And so the sun to the Earth distance is known as an astronomical unit, or to put it in terms of miles, that's about 93 million miles, or about 150 million kilometers thereabouts. Well, it turns out that over here is where the James Webb Telescope is going to be. It's in this portion, this point called L2, which is one of the few points of stability. It's called a Lagrangian point. It's a point of stability where the gravity is such that you can have a pretty stable orbit. And this object is actually going to orbit once every 168 days in this particular orbit here. And it happens to be 1.5 million kilometers away from the Earth, or just under 1 million miles away from our planet. So it's not like the Hubble, where it's over 200 miles above us. It's much, much further away from us. So it's not going to be as easy to repair it if something goes wrong. Okay, so the first image that came out was released, you may remember it from President Biden. Actually released this one on Monday, July the 11th. So the actual telescope went up into space Christmas Day of 2021. And so this is essentially James Webb's version of the deep field. And here again, every one of these points of light, except for the ones that have the diffraction spikes, where you have the 6 points, all those are stars. Everything else is a galaxy. And so to kind of put things in perspective, the amount of material it covers on the nighttime sky, take a grain of sand, if you could get it like on the end of your finger, and hold it out at arm's length, and you're covering about that much of sky, and you have a few thousand galaxies in this particular picture. So again, just amazing to me. One of the most amazing things about space is how vast it is, how we are one of many grains of sand, which is pretty awesome in itself. Now, the next day, they released some pictures as well, including the Carina Nebula that I started my slide set with. They also came out with this Stephan Quintet. So it represents 5 galaxies, of which 4 of them, so this galaxy, this galaxy, this galaxy, and this one, they all interact with each other. This one, I call it astronomy's version of a photobomb. It's there, it just happens to be there, it has nothing to do with the other 4. But these other 4 happen to collide with each other. And one of the things that the James Webb Telescope wants to figure out, we want to kind of fill in the gaps of what happens with galaxy collisions. Like, we see what's happening from our perspective here, well, what happened in the past to kind of draw them together? So that's one of the things that the James Webb wants to figure out in the future. Then this image is of the Southern Ring Nebula. So I like this image because it kind of compares, because I like to compare different telescopes to each other. So the left-hand portion is what the Hubble took. The right-hand portion is of the same Ring Nebula. And so you see the different amount of contrast and the amount of detail that you see on the right. That's because you have a visible plus an infrared image coming together for the James Webb Telescope. So everybody, this particular nebula, the Ring Nebula, the Southern Ring Nebula, represents what we call a planetary nebula. So that's where you have a low mass star that comes to the end of its life, pressure overcomes gravity, it explodes, and you have this nice, beautiful creation. So it turns out a lot of the beautiful pictures in astronomy come from destruction, but that's how it works in astronomy. So here's a question I wanted to post on Facebook here. So, because we're going to talk about exoplanets a little bit. So how many exoplanets, or planets that have been outside of our solar system, have been discovered as of tonight? So I'm interested in what you think.
And I'll keep an eye on the chat and see if anyone wants to answer.
All right, thank you.
All right. Someone said a plethora.
I love that word, plethora. It's a bunch,
I, I
yes.
I think you were probably looking for something a little more numerically precise,
Numerical,
but
yeah. A
plethora, that
number, yeah.
works. That
Yeah.
works. All right. I think plethора's winning. Want
Okay,
to
plethora wins. Okay,
want to
cool
give
deal.
us a number
I'll,
that defines a
yeah,
plethora?
yeah, I'll give you a numerical answer. It turns out 5,084 as of tonight. So think about that. Yeah, all these planets outside of our own solar system, 5,084. Now, what are these planets like? Are they Earth-like? Are they Jupiter-like? Well, one of the ones that was picked up by the James Webb Telescope, where they collected data, they actually collected both spectral data, so essentially using the Pink Floyd experiment, I like to call it, with the white light and the prism. They also collected light, which is called photometry, essentially measuring a change in brightness. So this curve that you see in front of you is showing the change in brightness. So when you have the star and the planet right next to each other, that's where you have the maximum amount of light for that particular system. And as the planet goes in front of the star, that's where you start to get this dip in the what's called the light curve, this particular graph. And so the bigger the dip is, the bigger the planet is, and it can help you get an estimate as to what type of planet this happens to be. This one, as the title suggests here, it's a hot gas giant, so it's a Jupiter-like planet or a Jovian planet. I like to call them, instead of Jovian, I call them the Jason planets: Jupiter, Saturn, Uranus, and Neptune. I just use that, and not meaning the if you're a horror movie flick, I don't mean that Jason. I mean JSUN, that different one. In any case, we found that this particular planet is about half the size of Jupiter, and it's much hotter than Jupiter. It's about 1,000 degrees Fahrenheit. And the reason why it's 1,000 degrees Fahrenheit, number one, its atmosphere, as was found by the James Webb Telescope, has a lot of water vapor, traps a lot of heat. Number two, this object happens to be point point oh four AUs away from the sun, to kind of put in perspective, from its sun, I should say. I'm sorry. So Mercury is 0.4 AUs away from the sun. So it's a factor of 10 times closer than Mercury is to our own sun. So it's quite amazing. This object kind of speeds around the planet, is a very hot planet. And so if you're wondering if you've never seen the WASP before, that means wide angle search for planets. That's what the WASP stands for. Now, as far as other pictures, I think this is a beautiful picture here. The Tarantula Nebula, and so just a couple of stats about that. It represents, whenever you see a nebula, nebula just means a cloud of gas and dust. In this particular case, it represents a stellar nursery. That is, you have stars that are being born in that as we speak. This one happens to be 340 light years across, and wow, 161,000 light years away from us. I didn't state this at first, I'm sorry. So 1 light year is the distance that light travels in 1 year, which is 6 trillion miles. And honestly, where do you hear trillion? One of two places, either math class, national debt, one of the two of those. It's where you hear the word trillion. So that's the Tarantula Nebula. But one I wanted to end with, my last picture I wanted to end with, is one that just recently came out a couple of days ago. So one of my favorite clouds of gas and dust is the Orion Nebula. If you take one of my classes, I talk about it a whole bunch, like twice, usually like twice a month or 3 times a month. I talk about it. So here you have the Hubble space image of it, but then notice the more detailed James Webb Space Telescope image. And so this is where the infrared comes in handy, because infrared cuts through a lot of that gas and a lot of that dust, and you're able to see a lot more detail and a lot more stars than you can in the Hubble image, which is mainly of the visible and the ultraviolet range. So I wanted to share this picture that just came out, like I said, yesterday. So to kind of end things here, well, what is the future of this James Webb Telescope? Well, it wants to find more information, especially it wants to fill in gaps that we have in astronomy. So we want to figure out, well, what were the first stars like right after the beginning of the universe, right after the beginning, the Big Bang? So the Big Bang Theory, as you know, started when Penny moved across the hall. Oh, I'm sorry, that's the TV show. My bad. Big Bang Theory, as in when it starts, the start of the universe. We also wanted to fill in gaps as it relates to the evolution of galaxies. So we have, of course, our still shots taken from the Hubble and the JWST, but we want to fill in the gaps as to how galaxies evolve, especially how do galaxies evolve after they collide with each other. We also want to figure out, okay, the birth of stars, how are these new stars born? Why do we have a lot of binaries, things of that nature? And the infrared cameras that are on the JWST will help with that portion. And then lastly, to find more of these exoplanets and figure out more about their atmospheres. That is, can we find any type of Earth-like planets that maybe happen to be what is called the Goldilocks zone, not too far away from its star, but not too close to its star. It's in the just right zone where it can actually have liquid water and possibly life. So that's one of the things that we want to study as far as the JWST. And with that said, everybody, thank you for listening. And do you have any questions? I would love to answer them.
All right. Well, thank you for that. It's great to see these images. Finally, I always tell people I have to admit I was a skeptic that this thing would ever get off the ground because it took a while.
Kept getting delayed. Yeah.
But it's been even better than anyone could have hoped, I think. So
yes.
I see a question in the chat that's asking how JWST is powered. Is it solar panels or a thermal radioactive source?
I believe it's solar. If I'm not mistaken, it's solar powered. Yes.
Yeah, and so
like the Hubble has solar panels as well.
Yeah, I'm pretty sure that's what that is too, with some minimal thruster capability. Oh, there's another question in the chat that says, so what was the number of exoplanets? I missed it.
Oh, sorry. 5,084. 5,084.
Yeah, a lot. A plethora, I believe, is what we said.
Yes, we can go
that was. But I always like to mention that, the first time that I taught Astro 101, we didn't really know of any exoplanets. So I always find this really exciting to look at.
And I always think about just think about the last 10 years since, when Kepler went up. And then, the amount of these exoplanets that were found by Kepler is a huge amount. It just grew the amount of, amount of planets that we have.
And it's a great example of observational bias, because if you didn't realize that Kepler was discovered so many, you'd think all of a sudden all those planets are in Cygnus for some reason because they just all pop into that field of view.
Yeah.
All right. So I have a question for you.
Yes.
So what are you most excited about that JWST can tell us that previous telescopes couldn't?
Ooh. I'm hoping that it tells us more about black hole interactions. That's my hope, especially if you're studying more of the galaxies, because most of your galaxies have those supermassive black holes. We can learn more about the gap. That is, there are supermassive black holes, and then there are ones that come from your heavy stars that blow up. But there's not much known about the in-between, like the intermediate ones. Yeah. So that's why I'm hoping that we find more about the intermediate ones.
All right, that's a fair answer.
What about you? Do you have one that you're looking forward to?
I do. I'm really intrigued by the ability to get better detections of exoplanet atmospheric compositions.
Yeah.
That to me is really, because we might even be able to get direct ones, not just the transit ones. And they already did proof of concept that they can do the transit ones, right? So I'm really excited about that. And the images they've gotten so far of Jupiter shows that JWST is actually going to be able to do some stuff in the solar system. So I'm excited about that too. So
the aurora that we saw for Jupiter, oh yeah, that was beautiful. I didn't show it in my slides, but yeah, definitely.
Yeah. And I'm wondering, will we be able to get maybe some infrared detections of stuff out in the Kuiper belt or pushing out to the Oort cloud that we haven't been able to get before. So I'm kind of, fingers crossed on that. But I'm looking forward to that. You're getting, there's a question about, do they eat galaxies? I'm assuming that's referring to the black holes. And so for somebody, so what does a supermassive black hole at the center of a galaxy do to that galaxy?
Oh, sorry. Yeah. So a supermassive black hole will essentially feast on whatever happens to be in its realm, what's called the event horizon. So yeah, each galaxy, or each stars, each planets, whatever happens to be in that area.
It's
And
got to be,
sometimes
it's
for
got to
the
be,
younger ones,
yeah.
kind of spits it out
I
with the
know. So
jets.
they kind of burp. They
Kind of
over
burp,
they
yeah.
they overeat and then they burp. But so we have a supermassive black hole at the center of our
Yes,
galaxy,
we do.
but I'm assuming we're not worried about falling in.
No, we're far enough away. We're good.
Okay. Yeah, that's the important thing there.
Yeah.
So
And I always tell I tell my students, Andromeda's coming. So, we got that
yes,
interaction coming.
yes,
Andromeda Galaxy.
yes. Yeah. All right. So I'm just looking to see if we have any more questions in the chat. I think we have handled most of them so far. Um, thank you so much for joining us, Professor Fitzgerald. It's
Oh, it is
so
my
exciting
pleasure.
to have you here to talk to us about JWST. It's really exciting, and I'm so glad that you did that lovely presentation. And
Yeah.
yeah, I think we caught the questions in the chat. So I would just like to thank Professor Fitzgerald once again, soon to be Dr. Fitzgerald, right? Right.
Yes.
And and once again, we will be doing Astronomy on Tap again in October. So subscribe to our page, like our page, so that you can keep up to date on that. And I guess we'll wish you clear skies. Have a good night, everyone.
Bye, everyone.